The purpose of this lab was to look at the motion of a star and use that information to determine the mass of a black hole. To do this, we used two physics concepts, first the momentum principle, and next the gravitational force formula. And through these relationships, we were able to identify the mass of a black hole through the computational model that I will walk through in this lab video. Below are the momentum principle formulas and the gravitational force formula. To start the lab, we were given initial values of data. First, we were given the mass of a star that is in revolution around the black hole. Then we were given the position of the black hole, and finally given the change in time, which is equal to 1 day, converted to seconds, equal to 86,400 seconds. After the first while loop that is used to calculate the velocity, we are able to start to calculate the mass of the black hole. By finding the velocity, we can then use the formula P equals mv to find the momentum of a star. Shown here, P initial equals the star mass multiplied by the initial velocity. And the final momentum equals the mass of the star multiplied by the final velocity. Now we have both the initial and final momentums of a star at a given time. By finding both of these values, we calculate the change in momentum and velocity as shown by delta V and delta P. We then use delta P to compute dP over dt, which by the momentum principle we know is also equal to F net, as shown in the opening of this lab report. Next, I found dP dt parallel by calculating the change in magnitude of momentum over delta t. Multiplying this quantity by p hat, we find F net parallel. Next, we have to find the perpendicular component of F net. To do this, we subtract dP dt parallel from dP dt. This is possible because if you add the parallel and perpendicular components of dP dt, you get total dP dt. Now, because of the momentum principle, we know that the final value for F net perpendicular is equal to dP dt perpendicular. To calculate the mass of a black hole, we take the magnitude of total F net multiplied by the magnitude of the distance between the star and the black hole squared divided by g times the mass of the star. This is the gravitational force equation previously shown, just algebraically solved through for the mass of an object. For the what does it mean question, we are asked to look at how net force is different from the rate of change of momentum. Although by the equations, F net parallel is equal to dP parallel and likewise for perpendicular direction, they describe different actions. F net predicts the forces that are acting upon an object, while dP dt is used to describe those net forces in the ways that the forces cause the object to move. Even though these values have the same magnitude, they are used to describe different actions. For the what if question, we are asked if we could find the new mass of a different black hole. However, because the motion of the star did not change, it means that the same forces are acting on the star. This means that the mass of a black hole did not change compared to the old black hole. If we look at the gravitational force equation, we know that it is directly proportional to the mass of the objects. And since the mass of the star did not change, the mass of a black hole could not change either if the orbit was the same.